In the name of Allah, the most gracious, the most merciful. All praise is due to Allah, and peace and blessings be upon the messenger of Allah, our master Muhammad, and upon his family and companions altogether. Now, as for what follows, by time indeed mankind is in loss, except for those who have believed and done righteous deeds, and advised one another to truth, and advised one another to patience. The rise of a nation. Let's explore the earth fault mechanism. How does ground fault current return to its source? Current flows in a closed circuit per Kirchhoff's law. A ground fault occurs when a conductor falls to the ground, creating a fault current on the relay, indicating a closed circuit. The question is, how does it return to the source? Ground fault current returns via two paths. The optical ground wire, OBGW, atop the tower, and the ground itself, unless high ground resistance necessitate parallel paths. Current divides inversely with resistance. With lower resistance carrying more current, ground faults in transmission stations are riskier than in generation stations because in generation stations, the current returns through a low resistance grounding network, preventing voltage increases on grounding conductors. The first path is via the optical ground wire, OBGW, at the tower's top. The second path is through the ground unless high resistance requires a parallel setup. Current flows inversely to resistance, with lower resistance taking more current. Current flows inversely proportional to resistance values. Ground faults in transmission stations are more dangerous than in generation stations. In generation stations, fault current returns to its source through a low resistance grounding network. In transmission stations, fault current returns through ground resistance from outside, causing voltage rise on conductors. We need low ground resistance for most fault current to flow through it. Current has two paths, through workers' resistance or ground resistance. Higher worker resistance and lower ground resistance increase danger. In transmission stations, the fault current that occurs far from the station returns through the ground resistance, extending from outside the station to the station itself, causing the voltage on the conductors to rise according to the increase in the return path resistance, potentially reaching dangerous levels for the workers, unless the ground resistance in the station is kept as low as possible. We need the ground resistance to be as low as possible or very low so that most of the fault current flows through it. The current has two paths, through worker or ground resistance. Higher worker resistance and lower ground resistance increase danger for station workers. This is due to increased resistance from safety shoes. What if a ground fault occurs in an isolated system with ungrounded neutral? How will fault current flow in a system not connected to ground? Theoretically, no fault current flows as the circuit is open. In reality, fault current returns via stray capacitance of transmission lines, but is smaller than if system were grounded. What if a ground fault occurs in an isolated system with ungrounded neutral? How will fault current flow in a system not connected to ground? Theoretically, no fault current flows as the circuit is open. In an isolated system, the circuit opens, but fault current returns via stray capacitance. A ground fault raises voltage on healthy phases due to line capacitances. Phase A's voltage becomes zero, and healthy phases' voltages become line voltage. If grounded through resistance, a ground fault shifts the neutral point, affecting phase voltages. If a ground fault occurs in an isolated system, it will result in a voltage rise on the healthy phases due to the line capacitances. Before the fault occurred, the voltage on each phase was equal to the phase voltage, as shown in this phase diagram, and the neutral voltage was zero. However, after the fault occurs on phase A, the fault current returns through the capacitances of the healthy phases, causing the neutral point voltage to rise to the value of the phase voltage, but it will be negative. This is because the voltage on phase A becomes zero after the fault, and thus the voltages on the healthy phases become line voltage, not phase voltage, and of course it is greater by the square root of 3. However, if the system is grounded through a resistance, and a ground fault occurs, the neutral point will shift from point N to point G, as shown in the diagram. This causes the voltage on phase A, where the fault occurred, to decrease, while the voltage on the healthy phases rises. Now notice with me that the voltage rise when a fault occurs in a completely isolated system is greater than in a system that is isolated through resistance. These systems require a higher insulation level compared to other systems. In summary, in isolated systems, if a ground fault occurs, it will result in a rise in voltage levels, may even distort the voltage waveform. Additionally, any imbalance in the system will create an unstable neutral point. So in this case, how can the relay detect ground faults in an ungrounded system, knowing that the ungrounded system can be referred to as an ungrounded system, an insulated system, or a three-wire system? Ungrounded system, insulated system, or three-wire system. The ungrounded system aims to reduce the short circuit current during faults by using capacitors with high impedance, minimizing the fault current. It also isolates the generator from external air fault, preventing current flow to the generator. Equipment connected to the generator remains stable. The recommended vector group connection for the generator transformer is star delta, with delta on the generator side and star on the line side. A ground fault on the star side won't transfer to the delta side. Isolated systems stop current from reaching the generator, preventing oscillations. Configure the generator transformer as star delta, with delta on the generator side and star on the line side. If a ground fault occurs on the star side, the zero sequence won't transfer to the delta side as it rotates within the delta. Similarly, the third harmonic current and its multiples, which cause generator overheating and overvoltage, also rotate inside the delta. We ensure stability and prevent operation during external fault. The vector group for the generator transformer is typically star delta, with delta on the generator side and star on the line side. If a ground fault occurs on the star side, the zero sequence stays within the delta, not transferring out. Similarly, third harmonic currents causing overheating and overvoltage rotate inside the delta without exiting. Notably, there is no phase shift between red, yellow, and blue phases for the third harmonic, similar to the zero sequence current with all vectors in phase. Just like the third harmonic current and its multiples, which cause overheating and overvoltage on the generator, they also rotate inside the delta and do not exit from it. It's important to note that there is no phase shift between the red, yellow, and blue phases for the third harmonic, just like the zero sequence current, and all the vectors are in phase. Harmonica is like a zirconia, and all the chords are negated. As every engineer knows, there is a close relationship between harmonics order and symmetrical component, as shown in this table. The harmonics of the first order, fourth, seventh, and others represent the positive sequence. Second and fifth harmonics represent the negative sequence. A second harmonic in current or voltage creates this sequence. Third, sixth, and ninth harmonics represent the zero sequence in both. The third harmonic is a zero sequence, but it includes various harmonic orders, as shown in this table. In a YY0 vector group, the neutral is grounded. A fault on the secondary side generates a zero sequence current. The sequence is on the voltage, while the third harmonic, 6 and 9, represent the zero sequence, whether it is current or voltage. The third harmonic is a zero sequence, but the zero sequence isn't just the third harmonic. It can include various harmonic orders, as shown in this table. In a YY0 vector group, the neutral is grounded. If a fault on the secondary side generates a zero sequence current, it mirrors on the primary side. The delta connection protects the generator from external faults, but internal faults require protection if the system is isolated. Two methods detect such faults with modern devices: residual voltage protection or sensitive air fault. Residual voltage protection, using broken or open delta connection, is common in medium voltage systems, as shown in the diagram. So the fault current will show a zero sequence on the primary side just like a mirror. The fault transfers from one side to the other. Therefore, the delta connection has protected the generator from external air faults. But who protects the generator from internal air faults if the system is isolated? There are two methods to detect this type of fault using modern protection devices. The first method is either using residual voltage protection, or the second method using sensitive air fault. Residual voltage protection uses the concept of broken delta connection or open delta connection, and this method is usually used in medium voltage systems where the residual voltage protection is connected as shown in the diagram. The primary side of the 3 VTs is connected in a star connection, while the secondary side of the 3 VTs is connected in an open delta. This relay detects any ground faults by sensing the unbalance that arises from them. If the three-phase voltage is balanced, we will notice that the voltage at the terminals of 59N is 0. 59 is 0. Balance. Voltages sum 0. Fault grounds phase, drops voltage, disrupts sum, trips relay, stabilizing resistor prevents resonance. If a fault occurs on one of the phases, that phase will become grounded, and the voltage of the phase that experienced the fault will drop to 0. Consequently, the vector summation of the three-phase voltages will not equal 0, and at that point, the relay will detect the fault and quickly trip the circuit breaker. As for this resistor, it is called stabilizing resistor, and it has been placed to avoid the problem of resonance or ferroresonance. The renaissance of a nation